volume from revolution. We have some function f, and we are told that we are going to rotate this function curve around the x-axis. So we're given an axis of rotation, and upon that rotation, we produce a figure of 3 dimensions. So imagine we're going to have some symmetry about that axis of rotation. So imagine they're supposed to be symmetric, poor drawing, but upon that rotation, we see that if we were to make slices into that 3-dimensional figure, we would get circle cross sections. So if we want to find that volume, it's going to be using that same slicing method or volume from cross sections as before. But with revolution, it just so happens that every time we rotate a single function curve around an axis of rotation, those cross-section shapes are going to be circles. So we know that from revolution problems with single functions, we're going to produce circular cross-sections, which is nice because we're whittling down our possibilities for our integrals. So going back to that volume from cross-section idea, if we integrate along some interval, so we'll say this is point A, and then over here is point B, we know that we have to integrate the area of our cross-sections. That's how we'll get our volume. And for this, we know that we're going to be making circles when we rotate a single curve around an axis of rotation. And we know area for a circle is pi r squared. So all we have to do is be able to come up with a formula for a radius at any point along that interval and define it in terms of our function curve. Now we know the radius is the length of the line from the center to some point on the circle. And the center of the circle is going to be the axis of rotation every single time. And a point that falls on the circle is going to be on the function curve when I make a cross-sectional slice perpendicular to my axis of rotation. So figuring out the length of this line is going to be, in this case, just the function output f of x. So what are we going to integrate? From a to b, pi f of x squared dx. There's your volume from revolution of the function defined in terms of x around the x-axis. Now let's look at another scenario where instead of rotating that function f of x around the x-axis, we're going to rotate it around the y-axis. So upon rotation, we'll still see some symmetry here around that axis of rotation. And when we rotate, we're still getting circle cross sections. So again, the idea is still the same. So we need to figure out a representation for the radius in terms of our function. And then that way we can get an area formula for a cross section and integrate the area formula for the cross section to get the volume of our shape. So we know the center of our circle is going to fall upon the axis of rotation. So distance from axis of rotation to the function curve will get us our radius. So if we're doing pi r squared as our area formula, if we're going to integrate with respect to y because we're revolving around y, we need to make sure our function is formatted properly. So if we're given f of x, or some function with an independent variable of x, we want to make sure we solve that thing for x so that it's now defined in terms of y. So we're going to have to reformat so it's f of y, and then distance, or the output, in terms of y, is going to be the length of that line there. So in this case, we're going to integrate from a. But how far up are we going to integrate? Well, they'll tell us. So, or if we have to find it, so be it. But at some point, I'll say b is up there. So let's say we're trying to find the volume from a to b of pi. Radius is f of y squared dy, right? We're integrating with respect to y in that case. Okay. So there's an example of revolving around x, revolving around y. A key thing that you have to pay attention to is if you're given a function in terms of x, make sure you're reformatting it as a function of y if you have to rotate around the y-axis. Now, we may not be necessarily rotating around either axis, but around some other line in the coordinate plane. So let's say we have our function f again, but instead of rotating around the x-axis, they want us to rotate around some horizontal line, say x equals c, whatever that is. Okay? So if we're rotating around that, we're still going to see some symmetry about that line. So down here, in the cross-sectional slice is still going to be a circle. Remember, the center of our circle is the axis of rotation. So calculating the radius is the distance from the function curve to that axis of rotation. So we should make a note of that. I think that's a good thing to summarize here. And we have learned how to find the distance between two curves. We're just going to take top minus bottom. So in this case, our radius is going to be the top function, f of x, minus the axis of rotation, which is a constant function. Oh, sorry. So this should be y equals c, not x equals c. Minus some function, constant function c. Okay? So make sure you know how to calculate the distance between these two curves. And that's actually what we were doing before, right? So if we were trying to find the distance between the function and the x-axis, well, the x-axis value is 0, so f of x minus 0, we didn't have to write it before. And same thing for that y-axis when we redefine in terms of y. So in general, again, we're trying to calculate distance between two curves, even if the curve is the x or y-axis of value 0. So we're going to do top minus bottom. Okay, and if we had to flip that axis of rotation so that it was above the function curve that's being rotated. So let's say we had to rotate around a horizontal line up here of value y equals c, and we have f of x. So if we're rotating around, we're going to see that circle value. We know radius is from the axis of rotation to the function. So in this case, our radius is going to be c minus f of x. Okay, so just make sure you pay attention to things like that. Always top minus bottom when calculating the distance between the two curves. Now, ultimately, because it is squared in the area formulas for your circle, top minus bottom, you might be able to get away with it, but it's a good habit to get into top minus bottom for the distance between the two curves, okay? So that is when we're rotating a single function about some axis of rotation. We know that the solid produced is going to have cross sections that are circles. We find a way to represent the area for the circle. We integrate the area for that circle. Over the length of that interval, we get the volume. So what else could we see? Well, this is the last thing that would pop up. Is let's say that we're given a region of space, R, and we have to rotate this region around some axis of rotation. Same principle. So let's say we rotate around the x-axis. We're going to see some symmetry there. And what we'll notice is that we don't get circle cross sections here. So the top, we're going to have that rotated around. And this thing's going to rotate around. So what's going to happen, and maybe I'll draw a better representation there, is that instead of circle cross sections, we're going to get this outer circle from the function that is furthest away from the line of rotation, and then this inner circle is produced from the function closer to the line of rotation, and we get what's called a washer here. So if you hear washer scenarios, that's what that is referring to. And to calculate the area of a washer, what we're going to do is calculate the area of the circle on the outside and then subtract the area of the smaller circle within. So what we're going to do is, knowing that areas of circles are dependent on radius lengths, we're going to call distance from the center of our washer to the exterior circle as capital R, and then this is lowercase r. So our washer area formula is going to be equal to pi capital R squared minus pi lowercase r squared. So when we have this scenario, we're going to have to come up with the capital R, or the radius of the larger circle, and then lowercase r, the radius of the smaller circle. Now, what is the representation for capital R in this case? So the outer circle is generated from revolving this top function, which we'll call f, and this bottom function we'll call g. So the larger circle is formed when we rotate f around that axis of rotation. So the distance, so we know the center of the washer, just like the center of the circle, is going to be found at the line of rotation, or the axis of rotation. So distance from axis of rotation to the function that's furthest away gets us our capital R, and distance from the axis of rotation to the closer of the two function gets us lowercase r. And we know distance between curves is top minus bottom, so our capital R is going to be f of x minus the axis of rotation value, which is, if the x-axis is just 0, so we don't have to write that. If we have lowercase r, it's going to be g of x minus 0. We don't have to write that. So what we're going to ultimately integrate, if we're working from A to, say, some point B over here, pi f of x squared minus pi g of x squared dx. If you want to, you can factor out a pi and then pull that out as well if you want to eliminate working with that constant in your integration. So if you just want to work with this, you can do that as well. So that's how you're going to find the volume when you have a washer scenario. Now, how do you know when you're working with a washer? Well, anytime they ask you to rotate a region of space about some line, so I'm going to introduce a new line in purple here. So let's say we have to rotate the R region around that new line there. And just like the example we started with, we'll be able to see this as well. But if there is a gap between the region of space you are rotating and the line of rotation, you're automatically going to produce a washer, all right? Because it's going to create that middle hole when we rotate around. We'll get that like donut looking shape. So in this case, if I have to rotate around this function, we'll call it C. Capital R in this case, let's make sure we're okay with that. It's going to be the distance from the line of rotation, axis of rotation, to the function that's further away. Okay, so it's not always the top function, it's the one that's furthest away. So this is our capital R, and in this case is your lowercase r. So make sure you understand that perspective when this is happening. So our capital R, the radius of our larger circle of the washer, is from axis of rotation to the function that is further away. And now how do we get capital R in this case? Still top minus bottom. So top constant function minus the bottom function, which in this case is g of x. For lowercase r, top function minus bottom function, which is f of x. So when we go to integrate from A to B to find this volume, I'm going to pull out the pi because it's pi capital R squared minus pi, so we can even write that over here, pi R squared minus R squared, like that alternative washer area formula. I'm going to remove that constant pi, and we're going to get c minus g of x squared minus c minus f of x squared dx. Okay. So there's another washer scenario with a line of rotation that is not the x or y axis. It's going to require you to calculate or represent the radius from that axis of rotation to those functions, and then it's going to involve that constant value. So just pay attention to those. And if you had to do this with respect to the y-axis, the only thing that changes, still all the same principles, but you're just going to need to make sure that your functions are redefined in terms of y. Yeah, that's the only thing that changes. But at the end of the day, volumes from revolution are just cross-section volume examples or slicing methods in disguise, because when we rotate around some line of rotation, we're either producing a circle if it's a single function, or we're going to produce a washer if it's a region of space that we are rotating and there's a gap between that region and the line of rotation. So we could have a region of space where there is no gap between that region of space and the line of rotation. We're just going to have circles again. We're not going to have a washer. So for instance, if they give us this region of space, which we call S, say, and they ask you to rotate that around the x-axis, you're going to see through that symmetry that you're going to have just circles again. You're not going to have a washer. Okay? So washers are only created when there's a gap between the region of space that you're rotating and the line of rotation. If there is no gap between, then you're going to get circles again. Okay? So those are the two examples you would see for revolution problems.